All right, part two. Here we go. Now you might have if I'm in class, usually somebody will raise their hand and say, "What does that 20 represent?" Well, the 20 is that line right there. And I'd say, "What do you think what is that line right there?" And somebody would go, "Well, that's the diameter." Of course, it's the diameter. That's the entire distance across. There is no reason to think that's a radius because there's nothing telling you it's broken in half. There's nothing telling you the 20 is only half this. If they put a dot right here and they move the 20 over to the right or left side, maybe you'd think that's a radius. So if this is 20, radius is 10, pretty straightforward. Take the radius and square it, you get 100 pi. Now if you have 314 on your paper, that's fine. I'm going to leave most of these answers in terms of pi. You can certainly turn them into decimals as well. When you're doing if you do a Schoology quiz, I'll probably say turn them into decimal just because it's probably hard to find a pi key on there conveniently. And if it's a practical application, forget pi. I want to get the actual decimal in there. But for this, it's actually easier to leave them all with pi in the answer. So this next one is kind of interesting. You've got two little circles that have been pulled out of that bigger gray circle. So you're going to want to find this white circle and this white circle and subtract them from the entire circle. So the question would be, what's the radius of the entire circle? I like to think of the diameter first. If this is 3, that means this is 3. If that's 2, this is 2. Which means the entire distance across would be 6 plus 4, which is 10. So halfway is about here, 5 units across. So this entire circle has an area of 5 squared pi. In other words, I guess I'm doing it that way. In other words, 25 pi for the entire thing. The other piece of it is I want to find these little circles on the inside. So if that's 3, that little circle is going to be 9 pi square units. 2 squared is 4 pi square units. And then like we said a minute ago, the entire radius of the big circle is 5. So that's 25 pi. Now none of these are my answer. I just want the shaded part, which would mean I got to subtract these 13 pi's from the entire thing. It looks like a little less than half of the circle was shaded. So as you see there, this is 12 pi square units total. This is probably 6 pi down here and 6 pi up there. Hopefully that makes sense. That's the area addition postulate. We're adding and subtracting parts of a triangle. Kind of the same idea in this last one. I'm going to give you more of these coming up later next week. This was a circle. Somebody ate most of the circle. I want you to assume that's a right angle. Otherwise, it's an impossible problem. If I was in class, I'd tell you, hey, that's a right angle right there. This is 8. This is also 8. This represents, if you were to spin this around, represents the radius of the circle. But it's not the entire circle. That's only 1/4 of the circle. So, if you did 8 squared, you get 64. It's not the entire thing, though. If you cut that into fourths, this is like a fourth of the piece of the pie on here. The area of just that shaded part would be 16 pi. That's kind of a preview of what's coming up later on. Sections of circles is what we're going to be doing in next week. Just want to show you one of those real quick. And again, I want to include some units on there because I love units. All right. On the back of the page, we've got this trapezoid. And we're going to show how the area of a trapezoid actually comes from cutting it up into triangles. Apparently, I'm going to jump down here to this thing on your paper, this question about a mid-segment. I doubt you had this last year. Usually we teach this in Math 1 and then re-emphasize it in Math 2. Apparently we don't do this. This is a good concept to have here. I want you to draw a mid-segment on here, and I'll show you what a mid-segment is before I tell you what it is. Try to draw a segment right there. Now, looking at that carefully, you can probably see I didn't just randomly place this thing. A mid-segment is always parallel with the parallel sides of a trapezoid. So I made sure that was parallel. Second part of it is I didn't just put it anywhere on there randomly up or down. I put it exactly halfway. In other words, if that was 2 units, this would be 2 units. If this was 3 units here, this would be 3 units. I cut this side in half. I connected that midpoint to that midpoint. Anytime you do that, you end up with a parallel line on here. So there's a definition of a mid-segment. It's a segment parallel to the bases that connects the midpoints of the legs. There's something interesting about mid-segments. I'm going to put some numbers on here. Let's say that was 10 centimeters, and then the top base was 16 centimeters. I like to just ask this question in class. How long do you think that midsegment is? And let people stew on that for about 30 seconds, and most people can figure it out. You know it's going to be more than 10 because it's higher up here, and you know it's going to be less than 16. Most people figure out it's going to be the number exactly in the middle. It's exactly proportional to those two. So I usually ask the question, how would you get this number from these two? Essentially, you average them. The length of a midsegment is always the average of the bases. So if this was 100 and this was 160, this thing would be 130. It's always the average of those two base lengths. It's going to be relevant here as we kind of find area here in just a moment. Be back in a minute on this section.